think about this.
Sorry.
Would you hear me?
No, there's some. It's not connected. Okay. Yes. Can you hear now? Yes. Yes.
Hola, hola. Okay. So, no. Hola, hola, hola. Okay.
So if you say hola,
Ciao. Okay.
I said hola. Okay, it's only Spanish. Hello.
This is not new.
It's okay for us. We can go Spanish.
Maybe if I just stay here.
Oh, we will try a solution.
I promise we try.
Try
Well,
again.
hola, hola.
Not the word. Just to be sure.
Will you hear me? Okay, that's fine. Okay. Okay, we know very well the mass of present-day stars, the distribution of masses of present-day stars. Either you could select salpeter or group IMF. We know more or less the characteristic mass and the general shape of the IMF. The problem with first stars is we don't have a clear idea about that. We think that they're mostly massive stars, but still the shape is something unknown. The Stefania's group in Florence is hardly working on that. And why is that important? Because the primordial IMF is placing strong constraints in all the subsequent evolution, the formation of the galaxies, the early chemical evolution, and also in pop-1 stars too. So this is something we should take into account, that we don't know yet what are the masses of the first stars. If we have a look to this picture of the predicted end of zero metallicity stars across different range of masses, we have this famous cartoon from Gregory Goosley. For low massive stars, you have white dwarf N until you reaches Chandrasekhar limit, then neutron stars until the Tolman-Oppenheimer limit, then you arise the black hole region, and there are more things happening related with penstability supernova and supermassive stars. If I have time at the end of my talk, I will comment something a little bit about penstability supernova. Otherwise, I refer you to Stefania's work. What is happening? First stars more massive than 0.8 solar masses, more or less, are already gone. Their expected lifetimes are smaller than the present age of the universe, right? We could potentially observe first star, zero metallicity star, if they are less massive than 0.8 solar masses. But the problem is, during the few decades, we thought evolutionary models suggested that no low mass star could form without metals. Carbon, nitrogen, oxygen, they allows the merging of cooling channels, and then the fragmentation of the globe allow for low mass star formation. There are recent works that pointed out that maybe even at this low metallicity, this low mass regime, first stars could form, but this is still an open question. But the general picture is not so optimistic, because or they are already gone, all of these more massive stars, or they didn't form at all. That's the reason, because we want to study the second generation stars, the stars that are direct descendants of these population tree stars. In particular, I'm going to focus in this talk in this mass range, something between 8 and 100 solar masses, roughly. Okay, and why is so important? First of all, with a complete chemical signature of these second generation stars, these unpolluted punctual stars, we could trace back and calculate masses of the progenitors, helping us to understand that the primordial IMF, and as I said, all the subsequent evolution in the universe. Secondly, they are direct proofs in the yields of the first supernovae. If we want to understand what are the yields of these violent events, we have to study in detail chemical composition in the atmosphere of these second generation stars. They also help us to understand the formation and evolution, the galactic halo. Pop-2 stars do live in the halo of the Milky Way. And of course, the early chemical evolution. In this cartoon, I show how at the very beginning, Big Bang is only producing primordial stuff, basically hydrogen and helium. After a few mega years, we think that the most massive stars are producing, because if they explode, say, as colloidal supernova are very efficient by producing alpha elements and less efficient producing iron peak elements. That's the reason we see in early chemical evolution of some systems like the Milky Way or other dwarf satellites, we see the famous alpha. Because at the very beginning, we have more alpha components, say magnesium, silicon, calcium, sulfur, oxygen. And then when subsequent generation of stars appear, low mass stars start to contribute to the general chemical enrichment in the Milky Way or in any other system. And type 1a supernova, after they become a white dwarf, one type A supernova start to contribute very efficiently by producing iron peak elements. So this is the game we see with the alpha N. Finally, after generation of stars, we reach our days and we see the current situation of the early chemical evolution. That's the schematic cartoon of how galactic chemical evolution actually works. There are some other like intermediate mass stars, AGB stars are producing also as process elements, but this just to show you an idea how it evolves. If we do galactic archaeology, it's like proving at different stages of this early chemical evolution, and we have something that to me is similar than the rings of a tree, that you could really learn what was going on at earlier times, just having a look for different proofs taken at different evolution. And these proofs are the first stars, the metal poor stars that I studied. Few words about nomenclature. I will say metallicity, and for those of you that are not familiar with these terms, I will consider metal poor in a logarithmic scale when a star is, say, metallicity contained is 10 times lower than our sun. Metallicity -2, we call it very metal poor star, is at 100 times lower metallicity than the sun, and extremely metal poor star -3, and so on, right? There are also taxonomy of metal poor stars depending on if they are carbon enhanced or not, if they are S or are process enhanced or not. We will comment on that if they appear during the seminar. Okay, it is quite challenging to study these stars. There are several reasons for that. First of all, these stars are extremely rare. In a simple halo field like this one, you could find only a few hundred. You can find only one extremely metal poor star in few hundred of this halo star, and one ultra metal poor star -4 in more than 18,000 stars. I am talking about halo field, right? It's not the distance. So they are very rare. Secondly, this I'm showing a high resolution spectrum of different 8 GK stars at different levels of metallicity. This is solar metallicity, a metal poor like star, extremely metal poor, and one of the most metal poor stars we know so far. As you see, the almost complete absence of the lines makes our life quite difficult because we are looking for the most interesting stars are those who do not show any metallic absorption, and therefore we are looking for something that we don't see. And if we don't see, it's better, but it's more difficult at the same time. This is because my job is because we are goal seekers, looking for something that is extremely rare, extremely difficult to find. They are typically distant and therefore faint, and you have to use highly demanded facilities, say 8 to 10 meters class telescope and high resolution spectrographs that they are always over demanded. So all of this together makes the field even more challenging. There are several groups all across the galactic archaeology field looking for metal poor stars. There are several ways to look for them. You have directly spectroscopic searches, which is expensive in terms of telescope time. There are photometric searches that is less accurate or less efficient, but it's cheaper, and this is the game. What we are doing, looking for these stars, is a methodology that is based in 3 different steps. It's like filtering possible candidates until you get your gold nugget. First of all, we were meaning into low spectroscopic surveys, multi-purpose, low resolution surveys, LAMOST, Fluorescent Sky Digital Survey, and some others. We mine into more than 10 million of objects, and this is an example of how it looks like. This is a high signature ratio because this star is brighter than its class, and we found this star which is -5 stars. This just based on the first filtering process directly from publicly available data. Second step is the best candidates, because of course this is not how we normally see almost fully noise data, and we have to select based in MCMC algorithm. We have to select the best candidates for the second step, which is go for higher signature ratio and intermediate resolution in facilities like the William Herschel telescope that is now with commissioning, and also OSIRIS at the 10 meters class telescope, Grand Telescope de Canarias. Within this step, we are able, because we select the candidates to be observed, we are able to identify and characterize ultra metal poor stars like this one, right? This is almost 1 million times less metallic than our sun, and this black is the data and red is the best fit. As you see, the signature ratio is huge, and the quality of the fit is also quite remarkable. All what you normally see in a spectrum of a metal poor star is the Balmer lines, right here, and nothing but carbon, because we know the more metal poor star one object is, the more metal poor one object is, the higher the chances to be carbon enriched. We will comment on that. And the last, or the more reliable estimator at these metallicities of the iron content is the calcium H and K line, which is the strongest absorption in the optical. This is what we use at this resolution and in this second step of the process. Finally, through all of these 2 filtering steps, we select the most interesting candidates and go for high resolution observations, either in the north with GTC or with the JAC, or in the south with VLT by means of UVS exuder if it's too faint, or in the North Horus. This is now is being recommissioned right now. But again, we have to, like all of you with your proposal, we have to fight with other very cool proposals. And since they are very faint objects, we tend to spend hours at the 10 meters telescope just for just one target. These are some examples of stars reaching between -4 and -5, and the lines now in high resolution. You see the lines. You are able to resolve some interstellar absorptions that could be affecting your lines, and of course, this is what we all would like to have at this point. Fast, really quick, an example of a star. The data we took in these 3 different stages to show you an idea how the process actually works. This is an Sloan spectrum in the optical band, and you see it's plenty of noise, and you barely see this calcium K line. So this is the first step. We went for the second step. We took 20, almost 30 hours of William Herschel telescope. It's a 4 meters telescope, and we took this cool spectra. This is the region around the calcium HK line, the G band, where the carbon CH features should appear, and the entire thing. And for comparison, this is so far the most metal poor star already known. When I say metal poor, we have to take into account that carbon is also a metal. We consider carbon as a metal. And it could be iron poor, but not metal poor, because it's plenty of carbon. So this, which is called the Kafau star, by Elisabetta Kafau, is so far not the most iron poor, but the most metal poor. That's the difference, and will play a role in when I want to talk about. And then in the high resolution, it is 12 hours of UVs, and we, in the strongest iron absorption in the optical, we don't see any sign of absorption. So we were only able to place an upper limit for metallicity, right? This is so far the most metal dwarf star already known. And that is important because dwarf stars are typically fainter at the same distance, but you don't have to deal with mixing process due evolutionary stage of your giants. So having a population of ultra hypermetal poor stars that are actually in the mean sequence is very valuable for the field. And this star, the 0023, showed also very interesting lithium absorption. Lithium is important because it's produced at the very beginning. Is produced due to Big Bang Nucleosynthesis, and there is a long-standing problem that we call the cosmological lithium problem. I will tell you a little bit about the lithium problem, and then we will go for the carbon isotopic ratio. They are the 2 main science cases I'd like to discuss with you. Okay, this is the traditional framework for Big Bang nucleosynthesis. There are basically 2 ways to get lithium. From basically, you need the fusion of a helium nuclei thanks to this and to this reaction, right? With this one, you are having beryllium, but beryllium is almost fully converted into lithium. So through these 2 channels, 10 and 7, we are having the tiny amount of lithium that is produced during Big Bang nucleosynthesis. Then, if we assume standard cosmology, if we assume cosmological principle, isotropy, and the general relativity, so we arrive for the Friedman equation, we arrive to this, and we can define the baryon to photon ratio. This is at the end This is the baryon to photon ratio, which is proportional to the omega baryonic. What's the game here? If we consider Big Bang nucleosynthesis together with standard cosmology, lambda CDM, we could predict the primordial production of all these species: deuterium, helium, and lithium. Okay. Then, thanks to cosmological observations in the acoustic peak of the CMB with WMAP, Planck, or all of these missions, you could derive or you could measure the omega baryonic, which is proportional to the baryon to photon ratio, and then you constrain the primordial production from these elements. The point is, we could measure deuterium at high redshift in hydrogen clouds, and we could measure helium in nearby metal-poor galaxies. The agreement between cosmological observations and the predictions by using this framework are quite remarkable. So they agree like almost perfectly. What's happening with lithium? Primordial lithium is measured in the atmospheres of these first stars. This is the prediction, and the astronomers, observational astronomers, during the 80s wanted to measure lithium in this POP2 star to confirm or to measure the primordial production. This was the general picture back in the 80s, when this is elemental abundances are measured in logarithmic scale. So this is a Dex scale, this is 2, and this is against temperature, and this is against metallicity. As I said, in the 80s, in halo stars, there were a first brave attempt to measure lithium in halo stars, and they realized that there were almost a constant value all over the temperature and all over the metallicity until the galactic contribution by nova, spallation, and other process becomes significant. But the point is, at earlier times, at the earlier epochs, lithium appears to be constant. So scientists at that time said, okay, we are seeing primordial lithium. But when the WMAP measurement appears a few decades after all, we saw a huge discrepancy. Again, this is a logarithmic scale. They saw a huge discrepancy of more than 2-3 times more predicted lithium in the cosmological observations that are actually observed in metal-poor stars. This is called the cosmological lithium problem. Actually, the Italian community is really engaged with it. Alessio Mucciarelli, Elisabetta Cafau, Piercarlo Bonifacio, also Lucas Bordone have done very relevant contributions to the problem. The star we discovered at metallicity -6 also show lithium. But before to show you the picture, nowadays, let me tell you that at some point when that happened, the community thought, okay, there should be something wrong with the lithium we're measuring in metal-poor stars. So maybe lithium is quite a weak element. With 2 million Kelvin, it could be destroyed. So it is expected that the stars, of course, in evolved stars, for sure, but it is expected that also stars could be depleting lithium. So many people started to look into what kind of process could explain this depletion, right? We even see this almost constant value in giant stars, Alessio's work too, that is quite, it is very well explained the lithium that is depleted due to the evolutionary state, and you could recover a few decimal dex below the plateau, you could recover also the value. And that's interesting too, because At that point, this is the lithium value, right? The lithium plateau value, around 2.2. All of these stars are the all well-known stars. And then when community were discovering even lower and lower metallicity stars, it was thought that at the end, maybe the lithium, this is called the meltdown plateau. And it was thought that maybe at the end, the abundance of lithium could be related with the low metallicity. So the lower metallicity, the lower lithium abundance. But then the star we found, and also this other star by Bonifacio 2018, showed that we are at even lower and lower metallicities, we are recovering again the lithium plateau. I have to say that these are only main sequence turn-off stars to avoid some evolutionary phenomena. And the question to me is again on the table, because the lithium plateau at least spans 4 orders of magnitude in metallicity. And if the stars were depleting lithium, it is no sense to do it in with a certain threshold. Why there are no stars in this huge regime? Again, this is logarithmic scale. We don't see stars right here. There should be stars. If it could be a common process depleting lithium, we should see a spread on lithium abundance from the original value down to wherever value you find in your metal poor star, right? So to me, this triggers again the discussion of the lithium plateau and the long-standing cosmological lithium problem. Of course, there are explanations for all flavors. There are people asking for further theory, further physics beyond the standard model. There are some groups that are working in cross-section of less, say, secondary nuclear reactions that take place during Big Bang Nucleosynthesis. People also working in other mechanisms that could be depleting lithium in helostars. There are many papers, but still, explanation should also account for this huge gap we see here, right? We are now preparing a proposal for next week with another interesting object that it may contribute to the to this debate. Okay, cool, more or less. Let's talk about carbon. Carbon in metal poor stars plays an important role. The reason, as I said, is it is observed that the carbon abundance is higher or is getting higher towards lower metallicities. So the most metal poor star, the higher the chances to have it carbon enriched. In this plot, we call carbon hence metal poor stars, which is CMP stars. In this plot that is being discussed deeply in literature is absolute carbon abundance versus metallicity, and we can distinguish at least 2 groups. This group, which is close to the solar value, that shows 2 main features. First of all, most of them are binary stars with what we call a high carbon band, and they are likely S-process enriched. S-process, I mean strontium, barium, or yttrium. So while the other group, this group is placed in the so-called low carbon band and show no signs of binarity until a few years ago. They are not rich in S or R process. We call them CMP-no, because it's not enriched in S process, and CMP-S because they are enriched. The classical picture for understanding this plot is, okay, these CMP-no stars are the real descendants of these first stars, and they are reflecting the chemical composition of the globe from they formed. While the other group are likely binary stars who underwent a mass transfer from a former AGB company. So we cannot rely anymore in the fact that they are reflecting the pristine abundances from with which they formed at that time. So they are suffering mass transfer from an AGB companion, which is rich in production, is producing or were producing as process elements. And that was the real, like, super, well, for my field at least, the super interesting stars, CEMP-no stars. And that's the question we want to answer. Could we really think, or could we really say that CEMP-no stars are the truly and pristine descendants of the very first stars? We started a project led by Paolo Molaro in Trieste with the aim of proving that CEMP-no stars, the most metal poor stars we know, are not binaries. If they were not binaries, we could say for sure, if they are not, of course, evolved stars, we could say that we are looking at the original chemical abundances in their atmosphere. We selected this time is carbon over Phe. Okay, similar, same plot I showed, but this time is carbon over iron. These are the most metal poor stars already known in literature. They are just 13, 14 below minus 4.5. And we observe all blue stars in our survey using Espresso. Espresso is a ultra-stable spectrograph. It is designed by the exoplanetary community in order to detect radial velocity variation in host stars of exoplanets. So it's quite suitable for our purposes to try to detect binarity behavior, binarity systems. And this is when carbon-12, carbon-13 plays a role. Because I will not go into much detail, but we found that several stars, in particular this one and this one, that we thought that were pure CEMP-no stars, so single stars, not binaries, were not. We proved that some of them are actually binaries. Then it could happen that no mass transfer has happened. How could we know that? And this is where carbon isotopic ratio plays a role. Carbon there are just two stable isotopes of carbon in the universe. Carbon-12, which is the most abundant and is produced in every like helium burning star. Carbon-13 is less abundant, of course, through the triple alpha process. Carbon-13 is less abundant and could be produced in several other places. In the cold CNO process, in red giants or more evolved stars, and also through the hot CNO process in nova, supernova, planetary nebulae. An important point here is in an AGB star, a significant amount of carbon-12 is converted into carbon-13. Actually, it reaches an equilibrium of carbon-12 over carbon-13 between 3 and 4, meaning that the isotopic ratio is the carbon isotopic ratio is also an indicator of the evolutionary stage of a given star. So we measured, well, by using this espresso, we wanted also to measure the carbon isotopic ratio in order to prove or to see whether the potential mass donation from an AGB companion had happened or not. because if you see significant amount of carbon-13 in an evolved star, it means that this carbon-13 should come from a AGP companion. That's the idea. So this was the status of the literature before our survey began. Again, metallicity versus carbon isotopic ratio. But again, these measurements were extremely challenging. The reason is these are two of the most metal poor stars. I already mentioned them. And all lines you are seeing here, the clear lines, are C12 lines. They are quite prominent. We could easily measure. Take into account that, for instance, this object is 22 hours of VLT, right? So the quality of the spectra. Espresso is not a super efficient spectrograph, it's super stable. So it's not like US, that is super efficient by doing chemical analysis. But Espresso, with huge resolving power, could help us to see small bumps in these shadow areas which are carbon-13 absorptions. They are still tiny, you see them, but they're still tiny. But luckily, we have hundreds of carbon-13 lines that are resolved at this resolving power. So by fitting the whole G-band, we were able to provide a consistent value for this star. This is Sleep star, and an upper limit for this Northland star. Then and of course, the result surprises us. Why? The carbon isotopic ratio, the best fit, for instance, have a look to this. Best fit is carbon-12 over carbon-13, 87. That means that there is almost no significant amount of carbon-13, meaning that even being a binary star, the potential mass transfer from its companion, which is unseen companion, we can, even with a speckle photometry, we cannot, because they are quite distant of us. They are like 2-3 kiloparsecs away. We were not able to see the companion, but deriving orbital parameters for the binary system. So we know for sure that it's a binary star. That was a shock in the community, because this star is probably the benchmark star for the lowest metallicity regime, and the whole community thought during 2 decades that it was a pristine star. But we proved that there was a binary system, but at the same time, we showed that the carbon-13 abundance we see in this star like discard possible mass transfer from a binary companion. This is the game we were playing. So following this line, we went for the rest of the sample. It were even more challenging because we could not spend 20 hours of espresso with at ULTLT with all of this star. But by means of another MCMC algorithm that is optimized for this kind of spectral fitting, we were able, in some cases, to derive carbon isotopic ratio or place strong constraint on it. This is just to show you how the Gaussians look like. This is something that is traditionally very difficult in literature, because, okay, you can, with high enough resolution, you can derive carbon-13 for a solar-like star or mild metal poor star. But for this object that they have almost no lines, is extremely challenging. So we developed this methodology just suitable for this kind of measurement. And again, this was the status of literature before we arrived with our Espresso program. And then let me show what is at the time we started with this, what was the state of the art of the predicted galactic chemical evolution models. Well, we can discuss with Donatella after the talk about these models, but let me bring your attention to 2 main things. First of all, Of course, at the very beginning, the carbon isotopic ratio should be very high because firstly is produced carbon-12, and then you need significant amount of carbon-13 production to see this trend, right? But it comes from such a high values up to, say, below 100. Then complicate things happening. There are several parameters in these models, but then there is a smooth and decreasing, monotonically decreasing behavior at the really early stages, right? Until we reach solar system and we see even lower values in the interstellar medium. So we were expecting to find something that more or less matches with that. Again, this is how was the state of the art at the time, and this is what we find. This is metallicity versus carbon-12 and carbon-13. Important things that surprised us here. First of all, this is -6, -5, -7 metallicity. So these stars should form 0.5 gigayears after the Big Bang, something like that. No later. The values that are measured, we did. This is not our value. These were already available in literature. These initial values are surprisingly low, at least to me. That it should be quite high, as all the models, to the best of my knowledge, all the models I have seen predict high values. Then we see this trend. Apparently, this trend. Is it real? Well, we were discussing with Limongi in a conference about the fact that maybe stars, say, intermediate mass progenitor stars for these stars, say between 20, 25, 35 solar masses, they would produce some amount of carbon-13, while more massive stars, say 50 solar masses, 45 solar masses, maybe not. And this could be an explanation of this behavior. The problem is we are not taking into account rotation. There's something that Donatella really works on it because there are no models of zero metallicity with rotation. So spin stars, fast, low mass, low metallicity stars rotating are predicted to form significant amount of carbon-13. Then we see a decreasing trend, but less steep, like this one. Again. And then we arrive to this set of values. Well, this dashed line is the predicted equilibrium between carbon-12 and carbon-13 in an AGB phase. So all of these yellow squares are more or less where they should, because they are evolved stars and they reached the equilibrium between the CEMP-no cycle and the triple alpha process. So they are more or less what they should. Then you have these blue stars that they are giant stars that maybe have passed the first dredge up, but still we cannot explain the amount of carbon-13 they have. So they are the isotopic ratio is not close to the equilibrium value, but still they show a significant amount of carbon-13 that is not really predicted by theoretical models. And then you could say, okay, maybe the evolutionary models we are applying here are not really correct, and these blue stars maybe are not where they should, or maybe they are where they should, but then these red triangles that are main sequence stars, therefore not affected for any mixing process that brings carbon-13 to the surface. We can't explain why they are right here, right? And then you have the solar value, and then something like here, the ISM value. So the behavior we are seeing here is slightly different than the predicted models. That's the reason I'm here discussing, in order to discuss with Donatella how we could reconcile models with observations. But the interesting thing, I'm finishing more or less on time. Interesting thing is thanks to this CEMP-no survey, we were able to trace back to the very early chemical metal enrichment in the early universe. So all of these stars that they were already discovered by other groups, but we were able to measure carbon-12, carbon-13, and we proposed to use this isotopic value because nitrogen 14, 15, and oxygen 16, 17 is almost impossible to measure in metal poor stars. So we propose to work with this ratio and then try to understand what's going on in this part of the diagram, and then explain how the evolution up to solar metallicity actually happened. Well, this is more or less what I wanted to show you. So perhaps the takeaway point, apart of triggering possible discussion here, is metal poor stars are always worth to observe. They are messengers from early universe, and now with the new generation of spectroscopy surveys, DESI, WIF in the northern hemisphere, also foremost moons, we are entering in a very exciting era because many of these weird precious objects will be revealed. In few years, if they are found in few years with the ELT, we will be also able to investigate in detail the chemical composition. And I just mentioned two of the science case we try to address with this science, but there are many others. So galactic archaeology, the place of the art process production, which is under discussion since the 50s. So I think it's worth looking for these stars, worth to spending telescope time observing them, and worth to analyze and discuss the consequences of these findings. So that's pretty much all. Thank you so much, and I'll take questions.
Any question for David? Also online?
Thank you, very beautiful results. So maybe I have a question, but maybe it's not possible to answer. It's about one of the stars, the one that you found to be binary, that wasn't expected to be binary. Do you think it's possible that it used to evolve in isolation and then only at a certain point was captured by a binary system via three-body interaction and it stayed there?
We were discussing about that, actually. It's a very good point. We don't know. I don't know if it's possible to know. Yeah, I don't know how could be the kinematical signature for that. I know exoplanetary community is also working in this, also capture planets, but it's absolutely out of my expertise, and I don't know if it is possible, but we were discussing about that possibility, which is very interesting, by the way.
Okay, thanks.
I was wondering whether both the high C12 or C13 in your binary and the value that is problematic for you that you find in the last plot could be related to the site of production of carbon-13. If I'm not mistaken, you assume that all AGBs should produce carbon-13. But isn't it actually restricted to a mass range, the one that with the hot bottom burning is able to mix and pick up carbon-12 and make carbon-13? So could it be that in the binary star, the binary that is there is not massive enough to produce carbon-13, and therefore you have a high value, solid value of the ratio? Mm. And could it be that in the other plot, again, it's a matter of range of masses of the stars that you're actually observing?
Yeah.
that they're not having carbon-13 simply because they're not massive enough?
Yep. Yeah, fair enough. It could be. I'm not an expert on AGVs, by the way, but I guess something higher than 4 solar masses up to super AGVs, maybe you know better than me, that they all produce.
Yeah, it's from 4 or 5, depending on the metallicity up. But then that low metallicity, I don't know. I mean, probably it's also a function of metallicity, the mass.
Yeah. The hypothesis we're working in is the metallicity of both stars within the binary system are more or less the same. So if we are talking about -6, -5 metallicity, the companion should be something like this. So yeah.
When you decrease the
metallicity, you pay for what is it? So depending on that, you may have the stars has already done an EGV, but without I don't know, depending on the mass.
Not because of the time, but because of the production. Yeah.
Yeah.
It's a good idea. Let me think about it.
There's maybe one question from online. I see one hand. Gajik, can you go ahead if you want.
Yeah, hi. Hola, David. A very interesting talk. I have a question which is not directly, it's a little off the topic, but I wonder if you are guys interested in those close binary objects like CVs. We now find a lot. We've now find some of them that show some unusual behavior from normal CVs. They have longer orbital periods and probably evolved secondaries, which probably had undergone unstable timescale mass transfer. So it is very difficult to detect the chemical composition because of the presence of accretion disk and other stuff. But we see a strange ratio of carbon to nitrogen. I wonder if it is something that might be interesting to consider in this context, and if you know anything about that. Thank you.
No, absolutely. It's super interesting. You are probably talking about more metal-rich stars, right? Right?
We are talking about carbon deficiency contrast to nitrogen.
Yeah. Okay. So the point is, so these stars are distant. We have calculated the orbital period in something like 35 years, so more or less. So we cannot really distinguish between close binaries and other scenarios. But absolutely, there are some weird processes happening when mass transfer donation that would have an impact in our results for sure.
Yeah, I understand that the objects I'm talking about are quite different from those that you are studying, but yeah, this mass transfer, influence of mass transfer on that ratio that you are determining is very interesting.
Yeah, absolutely. Absolutely. Thank you. So we have not enough evidence to really try to explain how the mass transfer could potentially happen, or it is something that we speculated with, but no, they're super distant. So not enough data to really say something smart about this system. So what I have shown is being cautious, the most we can say with data in hand. But absolutely, your idea would match with what we are doing and need to look into it. Yeah, thank you.
Thank you.
Any other questions?
David, sorry, just a clarification about your plot, carbon isotopic ratio as a function of the metallicity. When you talk about supergiant, you mean not supergiant stars, you mean giant stars after,
it is just a logic
after
of
the mixing, after the bump, correct? Okay.
Yeah.
So
We just,
pretty weird.
Yeah,
Yeah,
it is.
Way.
No, it's not. It is purely a logical.
Okay.
Purely a logical. A way of trace, you know, the evolutionary states, but absolutely, you are absolutely right. It's a very, sorry.
Upper part of the giant.
It's a very simple plot, actually. It's not taking into account many things. So it was just an attempt to come on. This was what we had when we started. So it was an attempt on say something in the earliest metallicity, at lowest metallicity. But of course, we have to refine this. We are applying for more data and try to include some other models, but the models, the available models in literature for zero metallicity stars, you know, they're not accounting for many things. I see from a theoretical point of view, it's difficult. This is just a way to show some behaviors.
Well, it's pretty reasonable. Well, at any metallicity you go, you expect the majority of the stars you look at are binaries. So having a diagnostic that tells you if binary evolution has an impact on the chemical composition you see or not, I think it's the only way to go.
Yeah, absolutely.
It's binary everywhere.
But yeah, I see.
Yeah, binary are there, and at least half of the star you look at should be binaries.
And at the lowest metallicity regime, there is still discussion on that.
Yeah, sure, but it would be, well, a bit strange to find no binaries because of metallicity.
Yeah.
No, so maybe the fraction is a bit lower, but I think there should be substantial at any metallicity. So
Absolutely.
This seems a clever idea to discriminate those that have mass transfer or not.
Yeah.
Other questions? Online, no. So, no. Take again.
Thank you for
Switch off the.
You consider only change.